Hi, and welcome to this presentation on runtime prevention of deserialization attacks. My name is Francois Gauthier, and this is joint work with my colleague, Sora Bay from Oracle Labs Australia. Let's start by defining the problem. So untrusted deserialization exploits do happen when an attacker can control the serialized object graph that is going to be used to reconstruct an object graph in memory. By controlling the serialized object graph, the attacker can also control, to some extent, the code that is going to be executed as the object graph is reconstructed in memory. And that, when the object graph is well crafted, that can lead to denial of service or remote code execution attacks. This kind of vulnerability was introduced in the OWASP 2017 top 10 as its own category, and in 2021 was merged in the broader injection category. Now, there are some existing approaches to help developers filter deserialization as it happens. An example of that is JDK deserialization filters. However, those filters do ask developers to block or allow classes individually as they are being read from the stream without any context about what is the actual graph that is being reconstructed. And what we found was that often it is the structure of the serialized object graph that defines if a serialized stream is malicious or not. Each and every classes taken individually are not inherently malicious or benign. So in this work, what we are showing is how we can use Markov chains to help detect the sequences of classes that make a malicious gadget chain to then prevent deserialization attacks. So let's have a look at the Java serialization format. Let's assume you have two different classes, timer task and comment task, with timer task having a runnable field that references an object of type comment task. If you were to serialize this object graph, you would obtain something that looks like this. First of all, you would have the class name in the stream, followed by a field description, and then the content of that field. In this case, it's a common task that also has a field of its own, which is a string, and so on. You can see that the timer task overrides the read object method. That is a very common entry point for deserialization attacks, because overriding the read object method allows you to override the default behavior or the default code that is going to be executed when this class is being deserialized. And so attackers often jump from an overridden read object method into another method, and so on. Now, the question is, what makes a good gadget chain? If we go back, way back in history, we can go back to Aristotle, who said that a whole is what has a beginning, a middle, and an end. And actually, if we look at malicious deserialization gadget chains, Aristotle got it right. So a good malicious gadget chains will have a method in the beginning that will be called upon deserialization, and then will hand control to what I would call linker classes in the middle that will be there to really just set the scene, like setting certain values in certain fields in such a way that when we reach the target method at the very end of the deserialization, then the exploit will be executed. Typically, this is like calling runtime.exec in Java that would allow you to spawn a shell and execute a command of your choosing. So the hypothesis we have in this work is that if we look at the sequence of classes and more importantly, the sequence of features that these classes have, we hypothesize that they will differ significantly between benign and malicious deserialization chains. And that should help us detect attacks at runtime. To verify this hypothesis, we model Java deserialization as Markov chains. So the first thing we need to do is to convert a class in a serialized stream as a set of features. So we simply just map a class to a set of features, and then given a serialized stream, we just look at each class in the stream in sequence, and then we can just abstract the whole stream as a sequence of feature sets, F1, F2, so on, up to F. Now, what are those features? We did actually do a manual review of why so serial gadget chains. This is an open source repository of known deserialization exploits. And we really looked at what are the features that make those classes so attractive to build a deserialization gadget chain. And so we identified 8 Boolean features, like does the class use reflection? Does it override read object? Does it override hash code? Does it have a generic field? And so on and so forth. To then abstract the classes as these set of features. I won't go into details about how deserialization exploits work. There's plenty of resources online, like Black Hat talks and DEF CON talks that go into details about how to construct those chains. In this paper, we are more interested in, about detecting them and preventing the attack. Okay, so now that we have the features, we can extract classes as feature sets, as I mentioned. And now we are ready to jump into actually modeling Java deserialization as Markov chains. So a Markov chain is simply a system that represents transition between different states. So it's a probabilistic state transition system. It has a finite number of states. In our case, the states map to different feature sets from different classes. And then it has a probability, an init probability of starting in any one of those states. And finally, it defines a transition probability matrix that just tells what is the probability of transitioning from a given state to another state for all the states in the system. And so this probability transition matrix fully defines the transition of a Markov chain. So now that we have a Markov chain, if we have an observed sequence of features, we can measure what is the probability that it was emitted by a given Markov chain. So let's assume that we have 2 different Markov chains, one that captures benign deserialization streams and one that captures malicious deserialization streams. So now we can calculate the probability that a given stream that is being observed at runtime was generated by the benign Markov model or by the malicious Markov model. The way to do this is actually pretty simple. We start by abstracting the first class in the stream as a feature set, and we then take the probability that the system starts in that particular state. That's B init F1. And then we look at the second class in the stream, and we take the probability of transitioning from F1 to F2, and so on and so forth until we cover the entire chain. That will give us 2 probabilities, one for the benign Markov chain and one for the malicious Markov chain. And then we can simply take the highest of the 2 probabilities to label an previously unseen sequence of classes. So as I mentioned, our goal is to build 2 different Markov chains, one that captures benign samples and one that captures malicious samples, and to estimate or to build those Markov chains, we have 2 different approaches. One is the empirical approach, where you have your training data set. You just measure the frequencies of all the transitions, and you apply that as your transition probability matrix. This works pretty well with large data sets. However, deserialization is typically a quite uncommon operation, meaning that the data sets we can gather are pretty small. So another approach is to use what I would call the Bayesian approach, where you are actually running simulations to determine a collection of Markov model that more or less equally well capture your training data. So now instead of going after just one Markov chain, we are going to build several of them And that will allow us actually to also measure like the confidence in our predictions. Good. I won't go into more details about how we actually do the Bayesian inference. This is quite technical. You can find more details in the paper. But the output of this whole simulation and sampling process is two different sets of markov chains, one for benign training data set and one for the malicious training data set. Good. Speaking of data sets, our malicious data set comes from the YSO serial public repository. The way we extracted the features for all the gadget chains in YSO serial was to create a Java agent using ASM to dynamically extract the features as those gadget chains are being deserialized. So we then just built a harness to deserialize those gadget chains. And so then the agent was just extracting the features from each classes in the chain. We apply the same logic to our benign application, which is Oracle Web Logic Server in this case, which is an enterprise system that is doing a lot of, that is using, heavily using deserialization for its common operations. So we did the same thing. We built an agent, we attached it to WebLogic, and then we exercised WebLogic to trigger deserialization, and then extracted the features from all the classes that were being deserialized. So this is a data set that we could extract. The malicious one has 37 unique deserialization chains. We could extract 227 unique chains from WebLogic Server with average length of 39 and roughly 17, and median length of 13 versus. Okay, so now that we have those data sets, we can actually build markov chains for the benign data set and markov chains for the malicious data set. And so at runtime, what we are doing when new gadget chains are being deserialized, the first thing we do is for each class of that is in the serialized stream, we will invoke this Markov filter function that will first extract the features from the class that is being read from the stream. Then we will just append those features to the sequence of classes we have seen so far. So this is how we keep a history of everything that has been deserialized from the stream so far. And then we calculate the mean probability that the particular sequence we have seen so far has been generated by the benign Markov chains or by the malicious Markov chain. And note that this is a mean probability because we have a collection of benign and a collection of malicious Markov chains. So we can take the average of all those probabilities. Next, we look at the confidence interval around those probabilities. This is where the t comes into play, this little t parameter here. It's really just controlling how many standard deviations around the probability are we taking. So the larger the confidence interval, the more conservative we are. And so what we are looking at here is, given the probabilities and their confidence interval, we are looking if they are overlapping or not. This is what this joint variable is holding. And so then if we reach the end of the stream and the probabilities with their confidence interval are disjoint, then we can make a call. We just take the larger of the two probabilities and say, well, this is malicious or this is benign, so it should be accepted or rejected. We are very conservative, so if we don't find this, if the confidence intervals are not disjoint, if they are overlapping, then by default we will reject the serialized stream. And finally, if the confidence intervals are disjoint and we have read enough classes from the stream, this is this parameter L, then we will also allow to prematurely interrupt deserialization if we find that the chain we have read so far is malicious. So we can prematurely just reject before we even reach the end of the stream. Okay, so let's look at the results of this algorithm. We did a 5-fold cross-validation experiment with our data set. And so let's start at the bottom with the empirical approach. We achieved a precision of roughly 73% plus or minus 14%. So not very precise, a lot of variability, but perfect recall. The training time is actually quite low, 0.7 seconds, which is really good. However, if we look at the Bayesian approach, and this, once again, this T parameter is really just the number of standard deviation we take around the probability, so that's our confidence interval size. If we go for basically no confidence interval, we achieve a precision of roughly 92% plus or minus 7% with a recall of 97%. So already you can see that precision is much higher using the Bayesian approach. But we're paying a little price in recall. If we increase the size of our confidence interval, as I mentioned, we become more conservative. So we will reject more benign chains. So let's look at T equals 2. We achieve a recall of 100%, just like the empirical approach, but we gain roughly around 16% of precision. The drawback of this approach is that the training time is actually much higher, so around 2 hours to train all those Markov models. So it's quite costly operation, but training is done only once, and then at runtime, it's really just a matter of calculating the probabilities, which is actually quite fast. In the algorithm, I mentioned that we can abort deserialization early if we discover that the chain we are reading is malicious, so we can abort early without reading the full chain and risking having the exploit being successful. And so what we're looking at here is how many classes from a stream do we need to read before we can confidently abort deserialization without producing false positives. And so we can see that it takes around 22 classes read from the stream before we can say confidently that, yes, okay, this is definitely malicious. If we read less than that, the precision actually drops. So to conclude this presentation, I would like to do a quick dig into the false positives that we obtained. As you can see, we had a precision of roughly 91%, so we did produce false positives. And we looked at them to figure out why were they reported as such. And so they roughly fall into the following categories. Some of them were using the Java transaction API. Some of them were doing networking operations, code instrumentation, remote method invocation, or were managed beans, which is basically a Java class that the web framework can use to dynamically inject values and keep state and so on and so on. Note that all of those categories are very attractive to deserialization attackers. In fact, historically, if we look at existing gadget chains, instrumentation has been used, remote method invocation has been used, networking has been used, and to some extent, managed beans have also been used to do deserialization exploits. So not saying that all of those false positives are exploitable, but they definitely have the traits of classes that are typically used by the attackers. This is all I have for you today. Thank you for your attention. Feel free to drop us a line if you have any question, and go to labs@oracle.com if you're curious to learn more about the work we do here. Thank you.